Good afternoon. We resume our lecture again. What we've done so far, I have it on a sheet here. You can see we discussed something called AQL, that is acceptable quality level as far as the user or the consumer is concerned. Then we had something called RQL, that is rejection quality level. Then we had something called alpha. Alpha is actually the risk for the producer. And then we looked at something called beta. Beta is the risk of the consumer. We looked at something called AOQL, which is the worst quality level that any kind of sampling plan will deliver to the user. And then we looked at a couple of procedures. One was called single sampling, when you draw one sample only, and you come up with quantities called N and C. N is the number of items that you pick from the lot. Lot is generally of size N, big N. And C is the control limit, which should not be exceeded if you want to accept the lot. Then we looked at double sampling, we looked at sequential sampling, and these are all going to guarantee the same alpha beta protection to the user and to the producer. At the same time, as we are going from single to double to sequential sampling, we are also trying to cut down on the total amount of effort that is required in trying to do the inspection in doing this plan. Now here what we are going to be focusing on is how to determine this N and C. This is what we'd like to focus on. How exactly do you go about finding N and finding C? That is going to be the prime goal for this session, this third session. The plan must protect both the consumer, the buyer and the supplier. Both of these guys, these parties have to be protected. Now if you look into the single sampling plan itself, it's a pretty straightforward thing. Take N randomized samples from there, and the lot quality is unknown, that is P. Number of defectives found by your inspection is little d. If little d is less than or equal to C, C is the control limit there, you accept the lot, otherwise reject the lot. Either you return it to the supplier or do 100% inspection, do rectify inspection and then take it on. But how do I find this N and C? That's going to be the goal for the designer. Remember, we had the exact formula given by the binomial distribution, with the help of which we could really do this. And there is a little problem here, given as 4 samples, 4 items are chosen from a population that has got a defect rate of 10%. What is the probability that exactly 1 out of 4 would be defective? Now I trust you can do this. This is going to be basically 4 choose 1. P is going to be this 0.1 raised to the power 1, and 1 minus 0.1, which is going to be 0.9 raised to the power 4 minus 1, which is going to be 3. That's going to be exactly this, and I could write this formula out for you, or we could do that. So that thing can be done the moment we assume our distribution to be binomial. We could do it otherwise also. I've used the same formula here, and I've put down here 2 PA values. One PA value is at the level of quality, which is P1. P1 is very close to your AQL. P1 is the same as your AQL. And P2 is the same as RQL in the previous lecture there. Beta is the probability of accepting the lot, which is at RQL level or P2 level. And again, this would mean that defect levels are still only up to C. Both of these are probability of acceptance, so I've got to have this limit there, D going from 0 to C and D again going from 0 to C, and I could do that. So these two expressions, these are now 2 simultaneous conditions that your NC plan, in fact your plan, remember your single sampling plan will require 2 parameters. One is going to be sample size N, the other is going to be your control limit C, control quantity C. Both of those basically will determine together these 2 conditions which are given here. And condition 1 is this, condition 2 is this. Let's see how we bring them together. We could of course solve these 2 equations for the values of N and values of C. We could probably do that. But as you probably know, solving these 2 simultaneous equations which are nonlinear is not going to be easy. It's going to be a hit and trial basically if we try to do it. There are practical methods for doing this. One is, of course, to convert this into a Poisson distribution and use the Poisson formula to be able to work this out. And I'm going to show you another method, which is like remember the old method that we used in thermodynamics. Many times we ended up using what we called a nomogram. A nomogram is basically the graphic representation of a number of equations. A number of equations can be boiled down to what we call a nomogram. That's what you have shown here. This nomogram basically is a relationship between what we call P and PA. On this side I've got PA, on the right hand scale I've got PA, on the left hand scale I've got P. P is your lot quality. Now what are the two conditions given to me? My PA should be 1 minus alpha. Remember now, if you remember the OC curve, this was to the left of the OC curve. This was near the peak of the OC curve. And that value of PA there should be equal to 1 minus alpha. Alpha is the risk. Alpha is the risk of the, who is this risk for? It is for the producer. He should not get good lots returned to them. And this has to be done at the AQL level. So this is one condition. One condition is just that. The other condition is the condition of beta. And beta is shown right here. Beta is PA at RQL level. Beta is the straight probability of acceptance of the lot. Now, together, of course, we can produce the OC curve. We can produce all kinds of things. Let's see how we determine N and C given these two conditions. I have the same graph here. I've got the same graph here on a piece of paper. I've got the same graph here on a piece of paper. And I'm just going to write on this so that you'll remember what these are. I'm going to write the two quantities. One is going to be PA and the other is going to be P. Those are the two scales. I've got the P scale and the PA scale. And the two conditions have to meet. One of them is this condition here, 1 minus alpha equal to PA at AQL. So what I do is, I'll have to assume some value of alpha and I'll have to assume some value of AQL. I'm just going to do that for you because I have to work this out. And I could do the same thing for beta. I could assume some value of beta and I could assume some value of RQL. Let's start putting down some of these values there. Let's make AQL equal to 5%, 0.05. And let's make the value of RQL to be equal to 10%. This is equal to 0.10. And let's put these two risks. Alpha is going to be, let's make it 5%. Therefore, 1 minus alpha is going to be, 1 minus alpha is going to be now, let's call it 0.95. 0.95. And the value of beta, let's make it 10%. So this is going to be 0.10. So I have quantities now which are specific. All I have to do is I have to draw two lines here that will take care of the two conditions which I showed you earlier. One is going to be true at AQL level, the other is going to be true at RQL level. So for AQL, what do I have to do? I have to look at the value of PA, that is 0.95, and that 0.95 is going to come. I'm going to put a small circle there. 0.95 is right there. Let's make it green there. That's 1 point there. That's 0.95 right there. That's the value of PA. And what is the value of AQL that corresponds to this? 5%. 5% again, I could put a point there and put it like this. And then what I do my magic. I have a pencil and I have a ruler and I join these 2 points. And I'll just hope that my lead is not going to break and my line is going to be this one. This is going to be my line. I drew a line and if it is too light for you, let me use the green line. So I'm going to use the green line and I'm going to give you that line there. This is one line. Now that line takes care of one of those conditions. That condition is what? 1 minus alpha is PA at EQL. AQL is here. So let me write AQL there. AQL. And on this side I've got 1 minus alpha. So that's going to be this quantity there, 1 minus alpha. Then I've got the other equation also. And what is the other equation? 0.1. 0.1 is going to be my PA. So 0.1 I have to find on this. 0.1 is right over here. I've got 0.1 there. And this is true for RQL. RQL is the same as P, remember, lot quality. So RQL is going to be 0.1, so 0.1 is going to be over there somewhere. If I join these two lines, I'll be taking care of the second condition. So let me join them. Let me join them like this. And they are joined. And I've got the other line now. Remember now, the first, which is the green line, will take care of my protecting the producer or the supplier. The black line is going to be protecting now the user or the consumer. At this point, which I'm going to mark with, I think a good color will be, let's put red. At this point, both conditions are satisfied. I satisfy the condition for this guy. Who is this guy? He's the user, and this is the producer. At this point, both are satisfied. All I have to do now is on this nomogram, there are markings for N and there are markings for C. So let me read the value of N. N turns out to be, in this case, somewhere here, which is 250. N equal to 250. And the value of, how did I find N? I just climbed up the curve, that's all. And I climbed down the curve this way, and I'll end up with a, let me do it carefully, I end up with here somewhere. And this turns out to be my value of C. This is the value of C. C equal to 7. Now what is the result of doing all this? I've got my sampling plan designed, and the sampling plan will be going like this. I have here N equal to 250, C equal to 7. And that's my single sampling plan. That's my single sampling plan. And the design is now complete. Now if I wish, I can construct the OC curve for it. And there's a very easy way to construct the OC curve once you've got this thing there. Remember the OC curve, it kind of comes down like this. And for that, what I have to do is, I have to rotate my little scale there. And I've got to rotate it between AQL and RQL. Oh, I did not put my RQL there. Let's put my RQL there. This is my RQL. And this, of course, is your beta. Beta is this value there. So I took care of alpha and AQL, and I took care of beta and RQL. And to find the OC curve, all I have to do is put it here and rotate it and keep looking at values of P and the corresponding values of PA. Values of P and PA. If I keep doing that, if I keep looking at those pairs of readings, I'll be able to construct my OC curve, and the OC curve will, let me just spoil this chart here. The OC curve will look like this. It will start at some point which is like AQL. It will end at some point which is RQL. And on this side I'll have PA. And to just make sure that you are able to see it, there is my OC curve. And I found these points. How did I find these points? All I did was, I pivoted. That is my sampling plan. Right in the middle, in that red circle is the sampling plan. I pivoted my scale. So I kept reading little p and PA pairs. I kept finding them, and I kept finding these points. I kept finding these points. these points I kept finding for the OC curve, then of course I join them. I end up with my OC curve also. And once I have the NC plan, I have this one and I have this one, my sampling plan is completely designed. So it's like a great way to get your quick and dirty plan. This nomogram is called the Larson nomogram. It's the Larson nomogram. It's a pretty famous nomogram. And this gives you the exact design. This gives you the exact design of the single sampling plan. No such easy method is available for the double sampling plan or the sequential sampling plan. Generally speaking, there you have to look up some tables, or you may have to actually use a computer and calculate all the OC curves and everything else. Those you should be able to do once you've written your software routines and so on and so forth, that you should be able to do. But this nomogram shown here is the exact method for designing what we call the single sampling plan, the SSP. Okay, let's look at some other procedures also. We go back to the screen here. This is exactly the same thing that I showed you earlier. I give you another example, and here again they've designed an OC plan, and in that red circle there, notice the red circle there, they show you how to do the manipulation, how to draw up the alpha, beta, AQL, RQL, and so on and so forth, and they show right there. So that's just an illustration of what we've done before. Now here's another approach. The military, of course, I don't know really. I do not know if the military ends up with a curve like this. I don't know. They might be doing it for projectile estimation and stuff like that. They might be doing that, or they might be doing it inside an airplane. They might be using some nomograms for navigation and stuff like that. Those they might be doing, target setting and so on. But as far as a device like this is concerned, this is best used in the office. It can't be used really out in the field somewhere, where there are trucks arriving and with boots and bullets and everything else, and there you've got to do some quick sampling to accept or reject what has been received there. So what you'd like to do is you'd like to have a quick and dirty way to come up with a sampling plan. And that is done by the MIL-STD-105E. This is a standard method that has been around for almost like 60 years now, or even more than 60 years. This was designed by experts at the Columbia University, and there was some resistance, of course, and people have spoken up against this. They have said that the moment you're going the acceptance sampling route, you're throwing away your idea of your philosophy of zero defect and so on and so forth, which is actually true. But it turns out in many cases, defect levels have not yet come down to the level of 6 sigma. They've not yet come down to the level of a few fractions in 1,000 or million or something like that. They've not reached that level. Defect levels are still at percent level. We find many parts and items which are still at that level there, which is like CP or CPK less than 1, which we'll discuss in another session. That's like something where 6 sigma is trying to go. But because not many people are at the 6 sigma level, people are saying we got to have some method that we can use here and now today with the kind of suppliers that we have. Our suppliers are not at 6 sigma level, so we need some method. And one such method is this, the MIL-STD-105E approach. Let's see how it actually works. There's a bit of history. It came from World War II. It was built around World War II. And these are standard methods, and they are a bit of a cookbook type. They say you find this, plug in here, look up some number there, then again move up to another table, look up something there, and you keep doing these things, you'll end up with your NC plan. Eventually the goal is still to get the NC number that we found using our friendly nomogram. We could do this without too much trouble at all. But the same thing is done now using some tables. And let's see how they do it. So take a look at the process. The process is this. Determine the lot size. Determine what lot size. What is the size of the truck that you have received? So what is the size of the truck? Once you know the size of you ask him how many items have you brought. He says, I've got 2,000 items there. Now you got to come up with your plan to be able to do that. So the first thing is determine your lot size and what AQL would you like to operate with. You ask these two questions. Of course, you ask the users for this. You ask the supplier for N, you ask the user for AQL. Then you try to decide which kind of plan I'm going to use. Is it going to be single sampling, double sampling, or what? What state of inspection would you like to be using? Would it be very stringent, or would it be normal inspection? Or will it be relaxed inspection? What would it be like? Then you follow through a certain procedure. You look up something called the table K, then you go out to some other table and so on and so forth, and you read off the numbers of N and C and so on and so forth. Let's try to walk this path. Choose the AQL, and determining AQL of course depends on the use that you have. Now if you look at quality, if there is a certain part there and you can probably tolerate a few percent defectives, you might just say, well, as far as pens are concerned, probably 5% defectives are okay in the lot. But as far as maybe these scales are concerned, not more than 1% should be defective. And as far as this mouse is concerned, probably not more than 1 in 10,000 should be defective. So you determine your AQL level by looking at basically what you'd like to be able to do. Once you've done that, you got at least one item taken care of, which is like your AQL. After you've chosen AQL, decide on inspection level. There are certain procedures given for it. Then you determine lot size. Lot size is found by finding the size of the truck, how many items it is carrying. Then you'd like to go to what we call the MIL tables. And one of the MIL tables is going to be the MIL-STD-105E table. It's a standard table that is given to us. You decide on the kind of sampling you'd like to use, single sampling, this is what we'll be using there. And then you find the appropriate table that will be used now in conjunction with the single sampling decision that you've made. And then you go out and work out the procedures. Let's take a look at some of these sample size codes. Let's say my lot size was 1000. So I'm just going to be writing some numbers here. Lot size was 1000. N equal to 1000. That's given to me. And of course, it then asks me to decide on inspection level. So inspection level, what inspection level? Let's take the easiest one. We'll say we'll be using general inspection level category 1. So category 1 inspection. Just for illustration. So I'll be using inspection 1. This is what we would be doing. So we've got 1000 there, I there. And if I do that, and if I take this plan, 1000 will fall in this range there, and general inspection will give me a code G. So these two things together, they give me a letter called G. G is a letter that I end up with. This G is to be used subsequently. G is to be used in another table. So what I do is I've got this G there, and then I go on, and I've already decided about the inspection level. So there we are at level 1, that we've decided already. Then we have to really see what we could do with our G. Remember, G is now going to be giving me an idea of sample size. So G will lead to N. G will lead to sample size N. G will lead to sample size. And how is this to be done? You go to the normal sample size, and you go to the MIL table, normal sample size. And there what you find, you've got G there. It's got a sample size of 32. So right away, I get my sample size N to be equal to 32. 32 is one number that I found in for my single sampling plan. Then what I do, now I ask the question, what about AQL? What AQL are we talking about? And let's take an AQL. I'm going to just pretend that I'm going to be taking an AQL of 1.5%. Let's decide AQL requirement to be 1.5%. Let's say this is our requirement. What I then do is I locate 1.5% on AQL. I locate that on the columns. In the columns I locate my 1.5, and from this G I draw a straight line there, and I come down to this, and I end up with two numbers there. One is 1, number 1, and the other is 2. Now here it turns out this gives me C equal to 1, because that is the acceptance quality number here, acceptance level. These many defects I can allow in 32 items. Out of 32 items, I'll allow at most one defect to remain. 0 or 1 would pass the lot. 2 or more out of 32 defectives. 2 or more defectives out of 32 would fail the lot. That means I'll have to return the lot. So now I've got a plan completely with me, and the NC plan by MIL-STD-105E turns out to be 32, 1. This is my final plan. That's my single sampling plan. And you could see how easy it is. All I did was I went through a couple of tables and I was able to get to this final table, and here I was able to get my N and C. Very, very easy. And of course I can, if I wish, I could use the old nomogram or some other calculation. If this is a finite lot, I'll have to use probably the hypergeometric formula. But if we assume this to be quite large as compared to my sample size here, I could assume this to be more or less infinity. And therefore, the formula that I could use here would be the binomial formula. And I could, once the binomial formula could be used, I could use this to construct the OC curve. Why do I need the OC curve? Because I'd like to get some feel if this plan is going to be sufficiently discriminating for me to tell between good and bad. Now let's review a couple of things here. Then there's something called the normal inspection plan, then there's the reduced inspection plan. Those tables are there, and if you wish you could do that. And there are some switching rules also, depending on the quality of supply that you're getting. There are some switching rules also, and I'll leave this on the screen for you as I do my talking here. So keep that in front of you. I'll do some talking to you. There are certain things which are actually not possible to do with the MIL-STD plan. One of which is, let's say you've got some beta that you'd like to impose. Beta, what is beta? Beta is a risk. Beta is the risk of the user, the consumer, ending up with lots which are at RQL level. Notice here, all we did was we looked at lot size. If you go back to the diagram here, we looked at lot size, inspection level, AQL. That's all. Nothing else I used, and I ended up with my NC. What about beta? What about the risk to the producer? What about the risk to the consumer? None of those things are really quantified here. For that, you have to go to the binomial distribution, work out the formulas and so on and so forth. You'll have to do that. So the MIL-STD plan does not actually tell you the exact risks. It does not tell you that. But by doing this switching, they have a switching method here. By this, what they try to do is, if you're receiving bad lots one after the other, then what it does is, it tries to protect you by making your sample size larger, which is like increase N or reduce C, both of which are then going to affect your alpha and beta. If you increase N, your curve is going to come down sharply. If you reduce your C, again the curve is going to go down very sharply. And therefore what you're doing is you're trying to move gradually toward that ideal curve. The ideal curve comes right down, then it goes flat like that. This is what you'd like to be able to do. Now it does not do that in any scientific or quantitative way. It does not do that. It basically gives you these switching plans, which is what I've got on the screen here. These switching plans will generally give you directional support to reduce your alpha and to reduce your beta. But the MIL-STD plan directly by itself, it does not give you any indication at all as to what sort of risk are you exposing yourself to. That is very unfortunate. There are people, of course, who have used these MIL plans and they've worked out those things. And you've got power curves for the MIL plan, you've got a lot of other things for the MIL plan, you've got the OC curves plotted for the MIL plan, but these have been done afterwards. In the original MIL plan, these are not there. MIL plans, by the way, they've gone through some revisions, and it turns out in the latest version, in October 2008, look at this last blue line here, the MIL-STD-105E has been replaced by MIL-STD 1916 by the US Department of Defense as of October 2008. And I've given you a particular thing, and I don't want to click here because I'm not really sure if the network is connected. If the network were connected, we possibly could see what all plans they bring out. And they give you a completely different set of instructions and so on and so forth. So now, if you were to choose, what would you do? If you're in a factory, and if you don't have access to engineers, if you don't have access to good, nice statistical handbooks and so on and so forth, if you do not have a book on quality control and so on, in that case, it might be easier for you to find either a Bureau of Indian Standards plan or a MIL-STD plan and use that plan to come up with your the schemes. It's also possible that you would, in this case, if there's a large amount of production to be affected by poor quality parts, what you'd like to do is you'd like to put some effort and understand this sort of stuff, and you try to come up with, basically, what you'd like to be able to do is you try to come up with an exact plan. So the OC curve is known and the protection is known and everything else is known. This is the exact way to do your job, your sampling plan design. Couple of other things are also important. It's very important for us to realize, it's very, very important for us to realize that AQL, RQL, these are quantities that should not be determined arbitrarily. They should not be found arbitrarily. For example, AQL is the level at which your factory can operate comfortably. And depending on your own effort in quality assurance and quality management and so on, you might like to reduce that AQL very close to zero. For example, suppose you're doing JIT. If you're doing JIT, the input to your system should be perfect. And there's no question of using sampling if you're doing JIT. Absolutely no question of using sampling. Because sampling will allow a few defective items to go in. Because you're not doing 100% inspection. The only way you can do that, if you do 100% inspection of the lots that have arrived, and then you release them one after the other on your JIT line, but then you're not really doing JIT. You're really doing a lot of work that should have been done by doing much better process control. This is something you've got to remember. Same thing goes for RQL. RQL also has to be related to the cost of production stoppage, because RQL kind of assumes if a few defectives came along, and suppose these were the pens that we purchased from the market, right? And who did we supply these pens to? We gave them to a drafting class. And they had a test. And they were using the same pens. And suppose these pens were at a high level of defect. Suppose the 10% were defective. That means every 10th pen had some defect. Or what about the 10th boy who ends up with that 10th pen there and he is not able to do his job? He's going to suffer as far as his grades are concerned, the exam is going to be incomplete and everything else. And think of the same thing happening in a factory. Suppose a defective part gets into the machine and it stops the machine. You got to dismantle the whole thing, you have to take it all apart and so on and so forth. Perhaps it has broken a few things and so on and so forth. So if you've got defective parts coming in and messing up your system, you better make sure nothing of that sort comes in. How do you justify that? How do you ask for higher quality? You work out in economics, you work out the downtime caused by a change that is required because a defective item came in. A defective item got into your system and that impacted your production system and it caused some major disaster. Either it stopped the machine, broke a tool or did something like that, or it just caused downtime. And this has happened so much. When I worked in a factory, there were so many occasions. At one point I was operating a can filling machine. And these cans, the cans were a lot like these bottles there. And those cans, they were made of cardboard. And sometimes the crimping that is done to make sure that the seal is there, that seal was not very good. And cans, after they were filled, they started leaking. And this would happen probably once in 200 or 300. But every time one of those cans got stuck in the machine, there was oil all over the place. And we had to stop, we had to clean up and so on and so forth. We'd rather pay double the price for the cans just to make sure we got good seals around in the bottom. Now this is the kind of economics that you have to work out, and you should do it well ahead of time and should sit with the supplier and make sure he understands your cost. Just as he's interested in not being returned, the good lot should not be returned back to him. That is like something that he should know. But he should also understand that it's not just that the pen is defective, so I throw a pen, I pick up another pen. What about the consequence of some kid who is not able to write his exam because the pen is defective, or he ends up getting a he ends up with bad grades because the pen smudged or the ink ran or did something very funny, and that's not really going to be funny for him as far as his performance is concerned. When would you use acceptance sampling? There are certain occasions when you got to do this. When you're doing auditing, for example, you might do some sampling there. Or when 100% inspection is too high, you might like to do some sampling there. Those are like occasions you'd like to do this. 100% inspection may also take a long time that you'd like to avoid. Of course, when you do acceptance sampling, you are exposing yourself to certain types of risks. So you remember, the moment you step into the world of acceptance sampling, your alpha and beta are both going to be greater than 0. They are not going to be 0. Therefore, you will end up with a few bad parts in your system as a user, or you'll end up returning some good lots back to the supplier, because again, you're not doing 100% inspection, and a few bad parts may affect the results one way or the other, because this is statistical sampling. So, what is the summary of all this? Let's take a quick look at some of these terms. Many basic terms that you need to know before you go into this. SPC is statistical process control, which means control of the real process that is producing these parts. So I'm pretty sure, hopefully, the machines for producing these pens are so good that they do not have to do basically what we call SPC. We'll look at SPC in another session. But SPC is something that is really not required when you're doing routine mass production. In today's day and age, SPC should not really be a concern. Your CPK should be 1.6 or 2 or somewhere there. If it is there, of course, then you are a reliable supplier. That's like something where, there's a shift taking place. Industry-wide, there's a shift taking place. Remember that path that I showed you. We are on an uphill climb. We are climbing up and up and up. We did everything based on inspection, which is what acceptance sampling does. Then we did process control, we did SPC. Then we would do DOE, design of experiments. Then we would do Taguchi methods. Then we would bring in TQM. Then we would bring Six Sigma and so on and so forth. And the march is on and on. And this will keep going till we reach perfection, till we reach complete satisfaction. It will be there. There were certain reasons when we would accept the lot. There were certain reasons when we would reject the lot. These conditions were given in the acceptance sampling plan as that little letter C. C was the control quantity. Complete inspection could be justified if the item was such that the defect could be critical. It could cause loss of property or loss of life. For example, you'd like to do 100% inspection there. AQL is the average quality level that you'd like to live with, that you could live with quite easily. LTPT is lot tolerance per percent defective. This is the same as RQL. This is something, even if one lot of this kind gets into your shop, it's like havoc, it's like nightmare. Various types of sampling plans are available, and you know certainly what sample plans we are talking about. You've got the double sampling plan, you've got the single sampling plan, you've got the sequential sampling plan, and there are many other plans that we've not discussed. There of course are the Dodge and Romick plan and the whole set of variable sampling plan. They are also there. These are methods that can be picked up very easily. If you've got a book on statistics or statistical process control, they'll tell you about all these plans. You've just got a window open for you. Now this window of sampling has been opened for you. Now what you have to do is get deeper into this. Pick up the basics you get from these lectures there. Then you get in there and you try to sort of see, do I understand it all? Can I apply it? Can I design a sampling plan? For example, you must try, I'm certainly not kidding, you must try to see if you could, given AQL, RQL and basically your alpha, beta, can I come up with my NC? Can I come up with that sort of plan? That would be a big, booster as far as your confidence goes. So we've got then producer's risk, we've got consumer's risk, we've got alpha, beta. These are the probabilities for that. Now the difference between defect and defectives. A defect is something which happens in a product. A defect is there, for example, if the clip does not close properly. So if I put it in my pocket, for example, suppose the pen goes flying. That means there is a defect in the clip. Or suppose the cap falls off. I have the thing in my pocket. and somehow I was running around, bouncing and so on, and the pen fell off somewhere. That also is not such a good, it's a defect in the design. And there could be other defects. It could be, for example, the tip could be defective. Now, defective is something that has got the property, that says some quality criterion is not being met. Then it's a defective item. An item is defective, and what it has is a defect. That's what it does. Then we've got something called attributes. Attributes are those quality characteristics that I can categorize between good and bad. That is like something I could do quite easily. And I generally use a go, no-go test for doing that. Now, in mechanical objects, when I've got mechanical objects, there's usually something like a horseshoe. And you bring in your item and you try to see, does it fit in or does it not fit into that thing there? If it does not fit in, it's a no-go. And if it goes in, then it's there. And there could be multiple set of these go, no-go gauges that eventually determine whether this is acceptable or not. That's one way. The other way to do is to apply some sort of a gauge. You take some gauge and you try to measure the item against that gauge. And you try to measure its length or diameter or whatever it is. So there I'm doing variables measurement. That's like another way I could judge quality, I could assess quality, and that could be another way to try to come up with a sampling plan. There are sampling plans that are based on variables measurement. Those are also there. We have then, of course, something called the average sampling number. It turns out that the single sampling plan requires you on the average to take the largest number of items to sample. Whereas if you look at the sequential sampling plan, it takes the smallest number of items that you require on the average to sentence the lot that has arrived. But there are some issues here. One issue is this, that the sequential sampling plan is a little difficult to explain to somebody else. And remember those curves that I showed you. I showed you a couple of curves going, from one end to the other. I showed you those curves. I believe I can find those curves for you again. Just one second. I'll find those curves for you. And it's important for us to realize that there are many instances when those curves become very, very handy for us. And they can help us stop the process of inspection very, very quickly. One curve is right here. One curve is right here. It's important for us to realize these are decision curves. And I may start my sampling with my single sampling plan. What will I do? I will right away take like these many items. And I'll take maybe, like I said, in that case, we ended up with 80, 90 items there somewhere. And that's a very large number of items to sample all at once. And unless you inspect them all, you can't really make a decision. Whereas in the sequential sampling plan, you can sample one item at a time. And then if you hit this line, you accept the lot. Or if you end up going this way, you reject the lot. And the chances are almost zero. There is a theoretical result that shows that chances are almost zero that it will end up going this way and never really end doing this. There's a small chance of doing that, but that probability is almost zero. So it's very important for us to realize that the sequential sampling plan is going to give you the smallest number of items to sample. That's something that is also important for us to realize when you're selecting between good and bad and so on and so forth. Then of course we've got the average total number inspected. What I've done is I've attached to this, I've attached a couple of other sheets which really define this concept of AQL. A percent defective, that is the baseline requirement for the quality of the product or the producer's product. The producers would like the buyer to design, the buyer is now the consumer. The producer who is supplying the parts or the pens and so on and so forth, he would like the buyer to design a sampling plan such that there is a high probability of accepting a lot which is coming in at AQL level. Because there really is no reason for us to reject a lot which is already at AQL level. Now this being high means alpha should be low. On the other hand, I've got this quantity called RQL, lot tolerance percent defective. This is the rejection quality level, and this is of concern to the user, to the buyer. This is of high concern to the buyer. And of course, the buyer would like to make sure that there's a very low probability of accepting a lot which is at RQL level. That means here beta should be low. This also is something that we should try to remember. There are two risks involved. These are the two likelihoods. Therefore, there are two risks involved. one of which is called the alpha risk, which is the type 1 error, or the producer's risk. What is this risk? The producer may actually have a lot that is otherwise fine. It is actually at AQL level, but it is turned down, it's rejected by the sampling plan. Because again, sampling is not, the moment you're using sampling, you're not doing 100% inspection. Therefore, that is something that we'd like to make sure we do not run into too often. Then of course, we've got something called type 2 error, which is actually the consumer's risk. This is now the buyer or the user. His risk is that he should have almost no lots brought into his shop that is at RQL level or the LTPD level. Therefore, he would like to have that beta to be as small as possible. A sampling plan is very powerful when it is able to reject most of the lots that are somewhat away from AQL. So it approaches the ideal curve. In fact, the effort should be by increasing your N or by reducing C, the effort should be you should try to approach as closely as you can the ideal curve. If you can approach the ideal OC curve, you are doing the best that is possible. The average outgoing quality, like I mentioned to you, it's very important for us to realize that there is something called the average outgoing quality. And look at this thing, no matter what sampling plan you are using, your PA is going to be pretty high when your quality level is pretty good. So if you've got 0% defective, your PA should be pretty close to 1. This is near 1.0. And your PA should be very close to 0 when your defect levels are really, really high. If you use this principle, and if you work out, this is the expression for AOQ. AOQ is coming out of your rectified inspection. When you look at rejected, rejected lots, but what you basically do is you remove all the defects from the rejected lots, and then you pass the lots. If you're doing that, your AQL curve is going to look like this. And there is going to be a certain point, somewhat midway, where there is going to be the worst level of quality that this sampling plan will basically try to pass on the average. This again is on the average, not for a specific application of the sampling plan. No, not for that. But if you apply the same sampling plan, same NC number, again and again to various different trucks that are arriving, various different lots that are arriving, you'll end up with an average worst level. And many times customers would not like to tell you about AQL, RQL and so on. They just say, well, there is a number, I do not want to exceed that number. I do not want the incoming lot quality to be worse than this. There, of course, you'll be using this plan there. And there are sampling plans that are based on this. This can be estimated quite easily from this. And this is what is shown here when we do basically when we work out the details of the plan. We should work out this AOQ, and if possible, we should also try to work out the AOQL. And that AOQL actually is a pretty decent indication of how good or bad your plan is. Now, good or bad is in the sense of discriminating or being able to act as a screen. What also is a concern many times is the amount of inspection you have to do to keep your inspection system going. And that gets into something that we call the average total inspection, the ATI number. The ATI number basically is the total amount of effort that you have to put into what we call the inspection effort. Now remember, if you look at the number of items that we have to inspect, we obviously have to inspect the sample. The sample that I picked, if I picked a sample of 3 or 4 items or 10 items, 20 items, I have to inspect them all. Without that, I cannot find D and I cannot compare that to C. N and C are the 2 parameters of a single sampling plan. Unless I know C, I really can't do anything. I can't really decide on the fate of that lot there. And C by itself is not good enough. I need to know D, and I compare D to C. Once I do that, and that actually means I must inspect everything that is there in the sample, all the items in the sample. That means I must be at least inspecting the little n items, and that's what I inspect right there. So if you look at the average total number inspected, this n is always there. Then you've got the rectify inspection, which means the lots that are rejected. 1 minus PA fraction of the lots would be rejected. Their size is n. This n has been inspected 100%, so I subtract that from this and I multiply this. This is the average number of items that I need to inspect in an overall basis. Now, what is this a function of? It's a function of PA. N is fixed, big N is fixed, this is fixed. But this PA depends on P. P is your lot quality. P is your quality of the input material. So little p determines PA, and therefore ATI is also dependent on PA. So it's not really true that this ATI will remain a constant number as you're applying sampling plan. It turns out, if you're generally speaking, if your lots arrive at reasonably good quality, your ATI number would not be very high. And this is something we got to keep in mind. We got to make sure that we bring my PA as close to 1 as possible. That means that will happen only if my little p, which is lot quality of the input, is as close to 0 as possible. Lot quality is as close to being perfect as possible. That means p value should be very close to 0. If that is there, of course, I'll end up with a small value of ATI, which is good for me. Then, of course, I've got something called the average sampling number. And as I mentioned to you, directionally speaking, single sampling plans, they require the largest number of samples, largest number of items in a sample. Then, of course, double sequential sampling plans will give you the smallest number of samples that is there. And then, of course, I've got double sampling, multiple sampling, or sequential. So there are choices available beyond my single sampling plan to be able to do this. And depending on economics and the complexity with the help of which you'd like to implement your sampling plan, you'd probably use either the single sampling plan or the double sampling plan or the sequential sampling plan, or perhaps some other plan, for example, the MIL-STD-105E. I've given you some links. I've given you some links here, and feel free to go in there and check out any of these things. I cannot really remember if all of them are active today. And let me just do one thing. I just clicked somewhere, and I'm not sure if the network is connected. It looks like the network is not connected. And with that, I may be able to bring out 1 or 2 applications which are dependent on this. They will take you to the point, no, it is not connected right now. So that's a little unfortunate. If it could be done, let's see if we could still do something. I got some calculator on. Let's just go on for a minute. I have, okay, what they've done is they've converted the old sampling plan to a MIL plan, and they have shown these things, and no, they don't really show, but it's possible that you are able to utilize one of these plans there. If I go in there, if I click there, then it gives me batch size, give me my batch size, and batch size in our case was, remember, 1000, and AQL we took 1.5, and type of inspection was normal, level inspection was 1, let's try to make it 1, and normal inspection, and let's submit. Let's see what results we get. We got 32, remember? Somehow we used 32 as our number there. And let me just see if I could find that. So this is going to be a confirmation of what we are doing. And that's not so bad. That's pretty good actually. That we ended up with, I have a feeling it was 32 when we used it. And 32 is the number there, and it turns out 1 is the 1 or less except the lot. So n is 32 and that is 0. This has come, by the way, from an online help, and that came basically from what we had there. We had this PowerPoint there. All I did was click that number there, click that URL there. So kindly do this if you wish to, and check out some of these things. It's also got a couple of other places where you've got other references provided to you. Those you could check out. I certainly appreciate your sitting through this session. It's been a little heavy for you, I'm sure. And there's going to be a lot of other interesting things coming along in the Six Sigma. We have reached about the midpoint of the Six Sigma program. and we've completed 20 lectures, and there are 20 more to come, and ones that are going to come include design of experiments and actual Six Sigma cases. Those are going to come down the road. Thank you very much. Thank you.